Thank you for coming today. I'm Evelina Gabasova, and I'll be talking about analyzing social networks with F#. And I'm a PhD student in Cambridge, United Kingdom, and I do computational biology. So what I'm doing normally is analyzing biological networks. But this is sort of my hobby project to look at real-world social networks, because they are ultimately much more interpretable than biological networks. So first I would like to talk for a moment about why should we actually do network science. So obviously first is my area of expertise, which is gene interaction networks. And with network science we can actually look at what genes are crucial in some biological processes. But that's not all. We can do disease spreading modeling. For example, right now with Ebola, that's a very hot topic. And people are modeling what would happen if Ebola got to big transportation hubs, for example, or even how does it spread between villages if it's infective in a way it is infective. Another interesting area of application is power grids. I know in the US there used to be some situations where some plants was overloaded and then there were big blackouts in big parts of the network. So people did quite a lot of research on how to balance loads in power grids like this. And it's quite a hot topic in Europe right now because Russia might stop supplying gas to Western Europe any moment. Right now the winter has been quite mild, so it wasn't a very big problem, but it might be a bigger problem now. So people are actually modeling how can we balance supplies from other countries like Norway or even from Africa, and how to balance it and how to get gas to most places. Also we can model, for example, brain connections. And another work I've done, you can read a blog post about it on my blog on software dependency networks. But today I'll be talking about social networks. And it's quite a nice area of data science, and in every area there is one canonical problem. So this is one canonical problem in network science. This is just to introduce you to the type of things we can analyze. And this is the Karate Club network. It's actually from the 70s when a group of social anthropologists went to study a karate club at some US university. And they went around and asked people, who is your friend, who do you speak to most? And this is the sort of network they came up with. And it's interesting because one thing, after they constructed this network, there has been an argument between two people in the club. And the club split into two different clubs. So these two are the leaders of the individual factions. And every person in the network has to decide which part they want to join. So these guys joined number 1, these guys joined number 34, and then there is the question who these guys join. And right now this is like a very canonical problem when you are doing community detection in software social networks. And this is another nice problem. And I'll be doing something similar today with a network I will extract from Twitter. And this is actually a real-world problem. A company in Hungary had a problem. There were certain rumors spreading inside the company, and the management had no idea how it's happening and why can't they get the true information to people in the company. So this company was actually composed of 3 parts. One was the management, that's the yellow one here, and then the pink and blue one were factories. And they... Sorry?
Looks like the management knows nothing.
Yeah, exactly. They hired social scientists to actually analyze their within company network. And the scientists went around and asked people, who do you turn to when you need an advice? And as you pointed out, the management wasn't almost connected to the factories at all. So they had no idea what's going on there. And they were looking for, the social scientists were looking for the most important node in the network. And they found out that the only one that's actually important, that's connected well to all people in factories, was actually a health and safety officer. And yeah, because he went around and talked to people, but he wasn't connected to the management at all. So after this analysis, they actually knew who they should talk to if they want to spread some news around the factories. And this is the sort of insight you can get when you do social network analysis. Okay, but today I'll be looking at Twitter networks. And Twitter has this funny notion of friendship. This is a terminology that Twitter uses. Who's on Twitter here? I am? Yeah, most people. So this is each individual user, and then you have followers that basically follow you, follow what you do on Twitter. And if you follow someone, they are your friends. That's a slightly strange notion of friendship that Twitter has. Slightly one-sided. When you follow someone, they are your friends.
So is there a special word when you're both a friend and a follower of the same?
No. You are a friend and a follower. No, because Twitter has oriented links between users.
Well, I mean, if I follow you and you follow me,
then you can be mutual friends. For example, on Facebook, the standard relationship is undirected. Because when you are friends with someone, that person has to be friends with you as well. But on Twitter, the relationship is actually directed. It's just one-sided. Okay, and I'll be looking at something called the ego network. And I decided to analyze the F-sharp community on Twitter, because I didn't want to analyze a network around any specific user, because that's a bit creepy. So I choose the organizational Twitter account, which is the F-sharp org. That's an account of the F-sharp Software Foundation. So if you don't follow F-sharp Software Foundation, you should, because that's the foundation behind the open source F-sharp. And the ego network around it are all those nodes that are either friends or followers of F-sharp org. And this will give me the set of accounts on Twitter that are interested in F-sharp. That's my assumption, at least. And I'll be looking at relationships between those nodes. And that's the so-called ego network. Okay, so now I will show you how we can actually connect to Twitter. Yeah, here's my Visual Studio. Can you see the code actually? Okay. So I will just connect to Twitter. These are very secret credentials, so don't copy them. And I will create a connector to Twitter. And I'm using an F-sharp library for Twitter connection that you can find on GitHub. And now I have a connector, and I'll look at what I can do. I can look at on connections. Can we actually turn off these lights off? Might be more visible then. And I can look at for connections or search for users or look at Twitter timelines. So let's look at users. And for example, I can look myself up. Oh.
I think I can only control how quick it is.
Okay, so what this piece of code does is that it sends a request to Twitter, and Twitter returns a JSON document. And inside the library, I'm using the JSON type provider from F-sharp. which gives me typed access to all the information that I got from Twitter back. So you can see here, this is actually the JSON document. Move it again. This is actually a JSON document that I got from Twitter. And I can access all the information that's in there by typing t dot. And now you can see that I have all the information about my account that Twitter will give me. For example, I can look at where my account was created. And it was on the Saturday, March the 8th, 1951, 2014. It's quite new. And I also know that it's a string. So it's very easy to actually look at data from Twitter. So I wanted to show you how we can actually explore other types of data, and I will look at some interactions on Twitter. So I'll just search for tweets, and this function, the only thing that it does is that it looks for tweets that contain a specific hashtag. And on Twitter, you can't get all the tweets that mention a hashtag. You have to search in batches. And Twitter will always return you up to 100 tweets for each request. And it also gives you only access to about 1 week worth of tweets. So I will try to find all the tweets that mention F#. So hopefully the internet is fast here. And then I will look at this piece of code. It actually takes the tweets that I will get from my request. And I just look at number of retweets and number of favorites that each tweet had. And I will look at those that did have some retweets or favorites. And here it's just printing how many requests I already did, and you can see that right now I am up to 1,000 tweets about F# during the last week. And that's all. So just to show you again, it gave me a JSON document, and I can look at all the data that I have about tweets. For example, where it was created, if there was any geographical location attached to the tweet, if it was a reply to some other tweet, and etc. But I'm looking at number of retweets. And now I can look at the probability that if you tweet something with the hashtag F#, that it gets retweeted or favorited. So let's see. Oh, and you can see that the probability is 90%. That's very high. I was looking at C# this afternoon, and that was just 75%. So tweet about F#. And I have a question for you. Who thinks that number of retweets and number of favorites are correlated? That means the more retweets you get, the more favorites you get as well. Well, it would make sense, right? So now I have all the data, and I can just call the Pearson correlation coefficient, and it's just 0.017. It looks like it's not correlated at all. But we can actually look at how the data look. And now here, on this axis, we have number of retweets. And on this axis, we have number of favorites. And you can see that there is a bunch of data where the correlation is actually quite positive, but there is a lot of tweets that don't get favorited at all, but they do get retweeted a lot. So it actually shows that there is some correlation, but you should really use a different model because the correlation doesn't tell you everything. But that's why it's good to visualize your data. I should really look at what tweets get retweeted so much. Okay. So, back to our social network. To actually construct the network around F# org account, I had to look at the nodes that are connected, that are either friends or followers of F# org, and then at connections between them. But the Twitter API has terrible limiting rates. They allow you just 15 requests every 15 minutes. So this is me waiting for the data to download. I was running it on a server, and typically when I needed the data, I found out there is some problem with the server. And then I found out that actually the data that Twitter gives you are not consistent. Because when some people close their account, they still stay inside the social network. They still appear in the search when you are looking at friends and followers of some accounts. But then you can't access their data. So if you ever download data from Twitter, be aware of this. So I'll just look at the current data. I'll be looking at F#org, and I will be looking at friends and followers. And you can see that what I'm getting back from Twitter are IDs of friends and followers. And this is actually where the F# type provider comes into play very nicely, because they most of them do fit inside one integer. But the more recent accounts fit onto 64-bit integer. And that's a problem when your program doesn't expect that. So it's really nice to have some automatic methods to determine that you really need something bigger than just an integer. Okay, but I got my data, and I can look at how many friends and followers F#org has right now. So it seems that F#org follows only 20 people. But how many followers? 1,871. So that's quite a lot. And now also how many friends and followers are in the actual ego network. And it's not straightforward. It's not just the sum of these two numbers, because some accounts can be friends and followers at the same time. So in F#, what I do is that I just append them and I create a set which takes care of all the duplicates, which is very easy. And now I know that it has 1,880 nodes inside the ego network. Yeah, then I was downloading the data about users and their connections, which is not very interesting, but it took ages. You can imagine 1,800 minutes to actually download anything. But when I actually downloaded the data, sorry, I will just show you. Yeah, I saved them into a JSON format because later I want to visualize the network, and it's easy to pass into any library when you have the data in a JSON format. and this is how I will represent the network. That's a pretty standard way how to represent networks that are reasonably small, actually, and that's the so-called adjacency matrix. And it's just a sparse matrix, which is made out of 0, but for every link between user I to user J, means user I is a friend of user J, I will get number 1 inside the matrix. And if there is no link, I will get 0. And this will give me a very big matrix. Okay. I will just load my data that I saved into the JSON format. You can see this is, again, JSON document. And I can access it through type providers. So, for example, for usernames, I can look at all nodes. And now I know that for every node I have name and an ID. And the ID is int64, but I can look at all the names. And these are all the names of all the nodes inside the Ego network. So you can see that using the JSON type provider, it's incredibly easy to access any information that you have in a JSON document. And in F# you get the same for CSV files. Yeah?
Something I noticed in F#, I often have to put parentheses around things that have dots in them. We didn't need to there though. N.name. Print F% as n.name. We didn't need to put parentheses around there. But I noticed often I need to put parentheses around things with dots in them.
Usually not when they have dot in them, when they have parentheses in them. Because this is just a single element, but if it was a function, then I would have to put parentheses around it.
Okay. If parentheses not the dot, thank you.
Yeah. Okay, so these are just some helper functions. And this is actually how I create the adjacency matrix. I will just go through all the links. This is, again, the JSON document. This represents the JSON document. And for every link, I will look at its source and its target. And I will assign it the value of 1. And all the other values will be 0. And then I will just pass it into a sparse matrix function that will create the actual adjacency matrix. And also here, because it's, again, the type provider, I get all the IntelliSense. So I can access the source or target. So here you can see my sparse matrix. You can see that it's very sparse. And it also tells me how much, and you can see that less than 1% of values are filled, which is why we need a sparse matrix. If we were representing something like this in a memory, it would get filled up very, very quickly. But with sparse matrices, we are representing just the non-zero values, and it's very easy. So why are we actually using the adjacency matrix? It's very easy to compute things like degrees. Just a bit of terminology. The in degree is number of followers of a node, which means number of nodes that have links coming into this central node. And an out degree is number of friends. That means number of outgoing links from node. And when we have things represented in the adjacency matrix, the out degree is just a row corresponding to every node. Because for every link we have, for every link from I into any other node, we will have 1 in this row, and 0 if there is no link. And the same for in degrees. Every in degree is just a column in this network. So what we can do is calculate the out degree just by looking at all outgoing links in the matrix and taking their sum. So it's very straightforward. And for in degrees, I'm again going through every column. We can also use matrix algebra. Sounds fancy, but actually to compute sum of every row, the only thing we have to do is multiply it by a unit vector. Because when we multiply them, we get a sum of this vector and this vector, which will just pick up the ones that are in this row. So this will be the out degree. And if we multiply it the other way around, we will get in degree. It's just the basic use of matrix algebra. And in F#, it's actually really nice that you can see how fast things are. You just type in #time and it will time every command that you put in there. So now I can look at how long it takes to compute the out degrees while we are going through every single row, and it takes 148 microseconds. And if I do the matrix algebra, it takes just 16. So it's 10 times faster actually. And that's because it's probably quite well implemented inside the math.NET library. And it's always easier to use this kind of function than to go through every element individually. And it behaves in the same way when you are doing matrix algebra in MATLAB or R. So now what I'm actually using now is the R provider, which gives me access to all functions in R that I can call from F# quite easily. And what I did is that I just plotted degrees of nodes. So for every node, I'm getting degree. That means, I'm not sure if I'm plotting degrees or in degrees. Yeah, I'm plotting in degrees. That means the number of followers that each node has inside the ego network. And you can see that majority of the nodes have very small in degree, but there are some that have a very large one. It's very hard to see in this kind of plot. But this is how it looks. This is the histogram of in degrees. And this is the same thing on a logarithmic scale. That means it's just the same values here, but they are scaled logarithmically. And you can see that there are many nodes that have very small degree. There are about 200 nodes with degree 1 in the network. But then there is quite a lot of nodes that have very large degree. And this is a very heavy tail that we have here. But this kind of shape that we get on the logarithmic scale is very characteristic for so-called scale-free networks. And the actual mathematics behind this is not very important, but they are the networks that can be quite well modeled by using model of networks growing over time. And I think it's quite well characterizes Twitter as well. And imagine people are joining a network sequentially. And if there are people in the network already, they will be getting more and more links, because people that come into the network newly, they will just look at other people in the network that are there already. And they will probably connect to those people that already have a lot of followers. So on Twitter, for example, you are probably accumulating followers just being there for a longer time. And these kinds of network, this is just a random network. This is an example of so-called scale-free network. And you can see that they are characterized by nodes that have larger degree than others. And these are so-called hubs. And they cause that this network is very robust with respect to random dropouts. So the thing that the F-sharp network is the scale-free network shows us that if people randomly drop out of Twitter, the network will probably stay connected. And it will be hard to disrupt it completely. And another feature of this type of network is that on average, your friends have more friends than you have. I'm sorry, it's true, but it's caused by those nodes that have very high degree. Because except for those nodes, almost everyone has friends that have more friends. Just because people connect to high degree nodes, that's all. But if you actually do this analysis on Twitter and look at degrees, you will find that this holds. Okay, so but the importance of a node in a network is not only the number of its followers. Because imagine you are being followed just by random people that imagine you are being followed by just your, say, high school friends, and then another of your friends is being followed by the President of the United States. That makes him much more important than you are, probably. So it's not just who follows you, but how important are the nodes that follow you. And one nice algorithm to actually look at this is the Google's PageRank. I'm sure you know it because Google uses it to determine centrality of web pages. But it can be used for any kind of network because it's just a very general algorithm for finding out how important each node in network is. So if you look at this picture, you can see that those little guys are not that happy because they are not being followed by anyone. But this guy is very happy because he's being followed by many other guys. And this guy is very important, he's being followed by many other nodes. But he follows this one, which makes him even more happy. So the main idea behind the Google's PageRank is the so-called random surfer model. And imagine a person sitting at a computer, browsing the internet, and randomly clicking on links. I'm sure that never happens in reality. I never ended up on some web page and not knowing how I got there. But this guy does that, and he does that for eternity. And sometimes he gets bored and he jumps to some completely different web page. And a PageRank is just the average time he spends on each web page. That means if a web page is important, if many other pages point to that one, he will end up there much more often. And also, if important web pages point to some other web page, he will get there more often as well. So that's just the idea behind PageRank. And this is just how to do it numerically. If we want to compute a PageRank of this node, we have to look at nodes that follow him. And the importance of each link is basically weighted by how many links are going out of each node here. And that's because if you have a very important node in the network, but it points to every other node, then each link is probably not that important. But if this node is very important, then it will pass its importance to other nodes along the link. Does it make sense still? And then each node will sum contributions from all its followers. Yeah, I don't want to go into too much detail, but the way Google does PageRank computation is through MapReduce. I'm sure you heard that name as well. And it actually translates into functional terminology very well. If we have some initial PageRank in the network, we will just map it along each link, and we will create pairs of keys and values. And that's basically the contribution that each node here passes along the link. And then we will just collect that by keys. And I will just show you how it looks in the code, because I think it's much more understandable. Yeah, and if you know the mathematics behind it, PageRank is actually just a stationary distribution over a Markov chain. But you don't have to worry about that. What I'm doing here is that I'm just defining a map function that for every node, for every link with a source node and a target node, it will just compute key and value pairs. Here it will be PageRank times probability of transition, and then yeah, it's just basically a map function. And then the second part is here when I'm grouping those key value pairs according to the key. That in F# is basically just group by. So MapReduce shouldn't be really MapReduce, it should be map group by. That's not very important. Yeah. And here the only thing that actually does something important is this line, group by. And then it just recomputes the PageRank. And it's an iterative algorithm, so I will just start with every node having the same value, and I will repeat the map and group by steps until it converges to some stable value. So this is the actual PageRank algorithm. I just take the initial values, I will run the map function and then the reduce function, and this whole code is just looking at if it converged or not already. So I'm not sure how long this will take. Yeah, I have to run the actual function as well. Okay, now it's running. And remember, it's network 1,800 times 1,800, which is not very big. Oh, it finished already. And it took only 34 iterations. But the more dense the network is, the longer it would take. But this network is quite sparse, so it was very quick. So let's look at who's the most important in the F# network. So luckily, the first position is Don Syme, the author of F#. Here Rick, the organizer, is the 6th position, which is nice. And the 3rd position is Miguel de Icaza, the guy behind Mono, for example. So I think it shows that the F# community is quite interested in open source in general. Yeah. If you are on Twitter and you are interested in F#, I'm sure you recognize some of these names. So I ran this analysis a few times already, always with a new network that I downloaded. And this is how it looked in February. Actually, time wasn't in the first position. And this is how it changed till November. And you can see that most of the accounts within the top 10 are the same, but they change position slightly. And another thing to notice is that the numbers in their absolute value are smaller now, the PageRank values. And that's because the PageRank just tells me, well, in the random surfer model, it will tell me the average amount of time the surfer spends in each node. So in this case, it gives me like the average contribution in the whole network. But because the network is growing over time, I think it had 1,000 or 800 more accounts now than it had in February. That means that the whole amount of PageRank is just diluting between more nodes right now. But you can see that it's more or less stable. Okay, and now I just wanted to show you how the network looks in reality. So, and what I'm using is the D3JS library, which is very nice for visualizing any data in the browser. It's a JavaScript library, and because I saved my data in JSON format, I can just directly pass it into the library. And what it's doing is that it's using a simulation algorithm to find a good layout for the network, which means first it starts with just a random layout, and each node is represented as a particle, which is attracted to other nodes slightly, but then also there are something like springs between them, which make them pull apart from each other. And by iterating this, you can find some reasonable good layout. But you can see that it takes quite a lot of time. The network is very big. But I can, if I manage to catch any node with my mouse, I will be able to look at the person that the node corresponds to. Come on. No, it doesn't like me today. Well, I will show you a slightly smaller network. That will be faster. And this is my network on Twitter. It's smaller than the F# one. But here you can actually see that it's not so homogeneous. There is one part of the network that's very densely connected, and then there is the other part which is kind of less dense. And when I looked at the nodes, this is actually the F# community, and this is the more machine learning data science people. And again, I can look at the individual nodes. Oh, this is community for F#. Yeah, Donsheim is there. So you can see that it's quite nice. You can interactively explore your data and look at what's what. And now I just wanted to mention one other thing that I did today, actually. I wanted to look at the community structure of the network around F#. And I decided to use the spectral analysis. Again, I don't want to go into mathematical details, but if you take the adjacency matrix, for example, here, and compute the eigenvalue decomposition, that means you compute the eigenvalues and eigenvectors, which make this property hold. And there are algorithms to do that fairly efficiently. You can get both a centrality measure and a community detection. And if you don't use the adjacency matrix, but something called the non-backtracking matrix, this is very recent research actually. I think they published it about a year ago. This is a matrix that's constructed on a non-backtracking paths in the network. If you want to know the details, we can talk after the talk. But when you do this eigenvalue decomposition, you will find out that the first eigenvector is correlated with centrality in the network. So here I just wanted to compare it with page rank. And Don Syme, the author of F#, is still the first in both rankings, but it's quite different on the other places. Yeah, sorry, Rick, you fell down in in this ranking. But it still makes sense. If you follow the F# community on Twitter, you will see that this ranking is actually reflects the centrality quite well as well as the page rank. But what we can do next is look at the other eigenvectors, and they actually represent the community structure in the network. And I was hoping to see at least some geographical structure. For example, the US community would be slightly different than the UK community. And I was utterly disappointed because it turns out that there is almost no community structure. This is the F# community visualized. And you can see that most of the nodes are very tightly grouped together in the center. So F# is really one big family, at least on Twitter. And I think the main conclusion of this talk is go play with data, because it's really easy to do it in F#. And one thing that really helps, at least me, are the type providers, because they give me access to all the files without actually having to worry about parsing the file correctly. And another thing is, this is something I was working with today. This is a code in R that I had to modify. It's not my code, it's someone else's. And when you look at something like this, you have absolutely no idea which variable is a matrix, which variable is a list, which variable is a vector, which is just a value. It's just completely incomprehensible. But in F#, with IntelliSense, you get types on everything, so it helps. It helps much more. Here I had to evaluate every single thing to actually find out what's in there, which is something that I don't have to do in F#. And that makes it very hard to go to something like this after getting used to F#. Okay, so thank you for your attention. And you can find the code that I used for this talk on my GitHub. This is my contact. You can find me on Twitter. And if you are interested in F#, in London we will have an F# conference in April, the F# Exchange. Thank you.
Could you explain real quick, or just give us an overview what the non-backtracking means?
Yeah. Can I use the whiteboard?
Oh, sure.
So, if you have three nodes like this, and they are connected, the non-backtracking matrix is actually a matrix over links in the network. So if I have three nodes like this, there is 1 in the matrix every time that A doesn't equal C. So it doesn't allow this sort of link, like immediately backtracking. Because the problem with spectral analysis with adjacency matrix or some other kind of some modification of adjacency matrix is that the nodes that have very high degree just obscure all the other signal in the network. But if we have the non-backtracking matrix, if we don't allow the immediate going back, then this effect is much smaller. And there are some proofs that it's able to detect communities up to like detection threshold. Yeah, and it's a very nice algorithm. Any other questions?
Have you tried IPython notebooks with the IF-sharp kernel, IF-sharp?
I didn't, unfortunately.
Well, I enjoyed that last couple of weeks, although today I was struggling with it. It was not responding properly. It tends to hang out quite a bit sometimes in some code. But
Well, sometimes I'm using FSLab, which is, well, it's still sort of experimental, but it allows you to put comments into your code in Markdown, and then you can compile it into a document. Yeah, and if you have any plots, it will just include them into the compiled report. But it's not interactive like the network, like the IPython notebook is.
Well, thanks a lot for coming.